I'd like to welcome you back to our discussion about empirical formula. And like I said before, we previously looked at our famous rhyme, percent to mass, mass to mole, divide by small, multiply till whole. We solved a fairly simple empirical formula question, and that involved barium carbonate. Now, as promised, we're going to get into a little more challenging work here, because the next kind of problem involves using empirical formula and some chemical reactions. So I'm going to step out of the way and allow you to copy as I speak here. And you can see in this case, we have an unknown sample that contains carbon, hydrogen, and oxygen only. It is a liquid. It is an organic chemical, not that you need to know that, but it contains three elements, carbon, H, and O. And we also know that it's burned in pure oxygen. 1.039 grams of CO2 and 0.6369 grams of water were obtained. And the question is, what is the simplest ratio of carbon, hydrogen, and oxygen in the compound? So this is the question. Now, I think it's valuable to draw pictures because we've all heard the adage that pictures are worth 1,000 words. And I just want to step through this with you. What have we got? Well, I apologize, this is my lame attempt at a Bunsen burner, and there's the mass of the liquid that we're burning. There's our pure oxygen, and it's a complete combustion. There's no mention of carbon monoxide or solid carbon, so it's very easy at this point. Underneath the CO2 and the water, I wrote down the masses that were given in the problem, and then we have to figure out the percentage of carbon in CO2. The reason for that is that when you think about it, in the original compound, all the carbon that was right here had to end up in the CO2. There isn't any carbon in water. So that makes sense. Likewise, all the hydrogen that was originally in our original compound had to end up in the water because there is no hydrogen in CO2. The oxygen, on the other hand, that we had here, combined with this O2 to produce oxygen here and here. So hydrogen and carbon are easier to start with. We can find oxygen later. Let's start with carbon. If we have 1.039 grams of CO2 produced, we can find the percent of carbon in CO2, which we've already done before. That's 12 divided by 44. 44 is the molar mass of CO2, and that gives us about 27.27% carbon. Well, we can find out very easily what 27.27% of our 1.039 grams is, and we get quite a small number, as you can see, 0.283 grams of carbon. So that kind of takes care of the carbon that we started with at the beginning here. Okay? Our next element to look at is hydrogen, and like we just did for carbon, we can say that the percent of hydrogen in the water is 2 over 18, which is a molar mass of water times 100%. That gives us 11.2% hydrogen. You probably remember that from a previous lesson. Very famous percentage. The mass of the hydrogen in this amount of water, which is very small, is 0.112, which is 11.2% shown as a decimal, times 0.6369 grams gives us 0.0713 grams. We're almost ready to figure out the oxygen, but I figured a picture might explain it. So this is back to our original sample. Whether you look at it over here or whether you look at it here, we started with 0.5438 grams, and we knew that there were three elements in it. Well, we've already figured out the carbon, and we've already figured out the hydrogen, so if we subtract both of those numbers from our original mass, lo and behold, you'll get the grams of the oxygen, which ends up being 0.1895. So when you go back to our original, we've actually now figured out the mass of all three elements in the unknown. Now we're ready to go back to our rhyme, although we're only going to use part of it here, we've already gone through the percentage part into the mass and figure out the empirical formula for this compound. So I'm going to erase the board, and then we're going to set up a table similar to what I taught you in the previous video. So just bear with me as I do this. Let's get a clean blackboard. You're going to need a little bit of room on your page to fit this in as well. At this point, it actually becomes more clerical than chemistry, to be honest. Let's see what we have here. Well, we know we've got carbon, hydrogen, and oxygen. So we're going to make a table just like we did last time. And the masses of these elements are given. The mass of the carbon is 0.283 grams. The mass of the hydrogen we just figured out to be 0.0713 grams. And by subtraction, we found the mass of the oxygen to be 0.1895 grams. So that's fairly straightforward. Remember your rhyme? Percent to mass, we're already there. Next step, mass to mole. Moles equals grams over molar mass. We know this. So if we look at carbon, that's 0.283 over 12, 0.011 if you want to be really accurate, and that's about 0.0236 moles. Again, have your calculator running as we go along. It'll make a lot more sense to you if you do that. Let's continue. In the case of the hydrogen, the moles is equal to 0.0713 grams. The atomic weight of hydrogen is 1.01 grams per mole. Notice I'm going a little more accurate here because we don't want to have a round off error. This ends up giving us a value of 0.0706 moles. That's a lot smaller than that one. Sorry, a lot bigger. If we look at oxygen, we can see that the moles of oxygen will be equal to 0.1895 grams divided by 16 grams per mole. And for the oxygen, that gives us about 0.0118. So we have figured out three elements in terms of the molar ratios. Now, this doesn't help us much right away because they're very small numbers. We got to go back to our rhyme. Percent to mass, mass to mole, divide by small. This is the key. We have to divide by the smallest of these three numbers, and that ends up in this case being the oxygen, doesn't it? So if we continue, we take our 0.0236 and we divide it by 0.0118. That's pretty close to 2. And that's always good to see. If we continue, 0.0706 divided by small, which in this case is a 0.0118 from the oxygen, this gives us about 6. Again, close to a whole number. This is experimental data, so sometimes you'll see decimals like 5.98 or 6.01. You can round off a little bit at this point. And finally, 0.0118 over itself, because it is a small number, is 1. We're almost done. We've done all the hard work. So at the end of the day, we can see that the ratio of carbon to hydrogen to oxygen in this question is 2 to 6 to 1. We don't have to multiply to a whole because each of these numbers is a whole number. And in fact, we're pretty well finished the question. After all of our work, the empirical formula is C2H6O. So there it is, my friends. A little more complicated question, but I hope it makes sense to you, especially after having built it up from the earlier empirical formula question. That's all we have for this segment. From here, we're actually going to start looking at the actual formulas of compounds, and that's referred to as molecular formula. Stay tuned for that. That's section 6.9 in your text, and you'll be happy to know the final section in chapter 6. So we've done very well.